Precursors, where this was really cultivated, and Europe beginning in 1200. All right, and what I'm going to do is to, is to really look at three topics, and I'm going to have a space-time map for each of these. I'll begin with Pythagoras' theorem and the origins of geometry. Okay, so in my mind, Pythagoras' theorem is the first theorem anywhere in the world which is, in mathematician speech, non-trivial. If you were given this and you were naive about everything, you would say, really? Why would that be true? That's bizarre. Okay, so let's talk about it. Okay, I'm going to use this diagram. I'm going to gradually fill it in the course of the lecture. More and more things will appear. So we have here, on the left, Europe, then the Middle East, then India, then China. And it goes from 2000 BCE to the present. Okay, so cuneiform tablets in Babylon, and that's actually positioned around 1800, which was sort of the high point of their work. Mesopotamia. Now, first of all, what's amazing is that we happen to know what they did. And you know, the problem with libraries is that they burn. And they can be sacked and readily destroyed. Cuneiform tablets have the marvelous property that if they're in the fire, it makes them really permanent. You fire the clay, and it is preserved forever. Whereas the poor Incas, who also, 3,000 years later, were developing in a very comparable way to Babylon, they had the misfortune. It all began with accounting, and they had the misfortune that they did their accounts with strings, and they tied knots in the strings and dyed them different colors, and they had these very elaborate things called quipu, which was the equivalent of cuneiform tablet, and they rot, of course. There's about a couple hundred that survive, and although the Jesuits did lots of great things, they didn't ever write a book about how the quipu worked, so it's almost entirely conjecture. Okay, so starting with Sumerians, they began to keep financial records in clay, first with actual tokens, and then they said, what's the point of the token? We just make marks on the surface of the clay. And what they were doing is they were doing accounting, and because people had grown up with all sorts of screwy things like 12 inches to the foot and so on, and they needed one set of accounts, they decided to use base 60, and they had a fully developed place value arithmetic to base 60. And they needed to tax their citizens. So that's a clay tablet, a reproduction of part of it, and that's a field plan. And the point is, what was the area of this guy's field, so that you knew how much tax you ought to pay. And likewise, sales, inheritance, and so on. This is the big reason to do mathematics in a lot of cultures. But they also needed right angles. So, for some reason, which is a mystery, there are some civilizations in which rather large towns have grown up without any right angles. But by and large, towns with right angles do seem to be preferred by almost all cultures. Of course, you've got to have vertical walls too. That's gravity. So, how do you get these right angles? Well, it's not clear, but the 3, 4, 5 triangle is, if you have lengths 3, 4, and 5, it's got to be a right angle. This might well have been the first discovery. But the more basic discovery is Pythagoras' theorem. Okay, but I want to make a point about this. Boy, would we love, as a mathematical community, to have poems written about us, odes, celebrating our, now this is from a tablet, the goddess Nisaba, who received literacy and numeracy from the great god Enlil as a wedding present. Nisaba, right, woman sparkling with joy, righteous woman, scribe, the woman who knows everything. She leads your fingers on the clay, she makes them put beautiful wedges on the tablets, she makes them sparkle with a golden stylus. The one reed rod. Okay, now we're talking about land measurement. This is, a rod is, I don't know, 12 feet or something, so this is a reed, a very tall reed used, the measuring rope. Now look, they make it out of precious jewels, lapis lazuli. a yardstick and a writing board that gives wisdom. This Abba graciously bestowed them. In any case, Pythagoras' theorem was really one of their crowning achievements. Now, you have this crazy idea from high school that Pythagoras' theorem is about right triangles. It's some weird thing because Greeks love triangles. Why? No. You have that's not why Pythagoras' theorem is the fundamental theorem of geometry. It's because if you want to know how far things are away from each other in the world, you lay out perpendicular coordinates, and once you have coordinates, you need to know the lengths of diagonals. You have, if you want a systematic measurement, you have to start by perpendicular coordinates, and then the distance between any 2 points is given by a simple formula, and it's because you have a triangle where the two sides are one of the two axes, this diagonal line, its length is the square root of the sum of the squares of the two sides. So it's really because it's the fundamental rule for distance in space. That's the reason it's so significant. And this tablet, which to me is really mind-boggling, shows that they're way beyond the Greeks. I don't think there's any occurrence in the Greeks of using Pythagoras' theorem in 3 dimensions. But in this tablet, they're taking a gateway in a thick wall, and they're computing the distance from the lower left outer corner of the door to the upper right inner corner of the gateway. So it's a 3-dimensional problem. And you do it with 2 right triangles. And here's the diagram, and this is a translation. It's kind of fun. The width of the gate, let eat itself. That means you square the number. The thickness of the wall, let eat itself. Heap them, that means you add them all up. Right? You see, its like side, let come up. What is the like side? That's the square root. If you have a square, that's called the like side. The 2 sides are equal. So its like side means you take the square root, and lo and behold, it comes out. So, right. Now, was this isolated to Mesopotamia? No, it was in Egypt, but nothing as sophisticated as that tablet of the gateway appears in Egypt. And some other, I'll give later on talking about algebra, some examples where you can see that the Babylonians, they could solve quadratic equations with no problem. But at least the material we have from Egypt doesn't demonstrate anything near the mathematical sophistication. But you see in this slide, do I have a laser pointer? He's holding a measuring rod there, a measuring rope, rather, for laying out fields. So these guys are going out to lay out the foundations of a building or something of that sort. But look here. This is Mohenjo-Daro, the Indus River civilization. And you can see that this, on the bottom left, is a reconstruction from the ground plans, and on the right, there's an actual photograph of the ruins. They were laid out on a rectangular grid. Now, there's tremendous trade going on, by the way, between the Indus Valley and the Mesopotamian civilizations. There are coins from both civilizations found in both places, so we know this trade is going on. So I think it's hard to conclude that these people didn't also then learn Pythagoras' theorem, but no one's been able to decipher the script. All right, so let's go on to stage 2 of Pythagoras. It comes to India, and the first actual evidence is from around 800 BC. This is the Vedic Civilization. And I would say it's rather probable that they learned it from the Indus Valley people who learned it from the Mesopotamians, that there's a historical continuity here. But historians, being temperamentally conservative, would sputter and foam at the mouth at this assertion. I don't know, it's hard for me to believe that. Now, the interesting thing is, there's gods are involved again, but in a tremendously different role. It's not the great gift of the gods to tell them how to read, write, and do arithmetic. Instead, the gods want to be fed. They're ferocious gods, and they want animal sacrifice. And a large part of the Vedas really deal with the rules for having a proper animal sacrifice and how they're going to please the gods. And these gentlemen here, this is a reenactment without an animal sacrifice. There was a marvelous veteran, Fritz Stahl, who went over there to Kerala, where some of the most conservative Hindus still live and practice a very traditional form of Hinduism. And they agreed to reenact this large sacrifice for him, which he recorded. And this is a photograph of them. You see the sacred thread over their shoulders. That indicates they're Brahmins. Now, the altar on which the animal was sacrificed is what's in the poster. This is the this falcon here. This is huge, by the way. This thing is going to be like 80 feet by 60 feet. It's a giant thing. It's made of these huge bricks, which are coming up to about 6 feet or so. And exactly the rules. This is actually a scan from this book, the Baghdad Sutra, which I'll talk about in a minute, in which it's detailed exactly how you're supposed to lay out the bricks. And on the left is a plan of the entire altar space, which is a huge area covered by a tent in which the sacrifices goes on and many, many rituals to take place. So this is certainly not what you think of as kind of the Enlightenment mathematics. So these are in these books called the Vedangas, the limbs of the Vedas, which codify this practice. And their geometry, which has a tremendous amount in common with the early books of Euclid for ruler and compass, is all about laying out an altar properly with ropes and stakes. So instead of a compass, you put a stake on the ground, tied a rope, and you drag it around until they intersect it. And this diagram there in the bottom left is the reconstruction of one of the parts of this particular sutra, in which you're laying out a square. And I won't go through in detail, but they start with one circle and another circle, and they find intersections. It's just like Euclid. And they're constructing a square, but they're doing it on the ground, on a big piece of ground. And here's the quotation in which Pythagoras' theorem is stated: the chord equal to the diagonal of an oblong makes the area that both the length and the width separately make. So that's precisely Pythagoras' theorem, stated approximately 800 BCE. So they had this fantastic tradition. Okay. Now, China. Now, Chinese history of mathematics in the early days is obscured by a very unfortunate fact. Mao was not the first person to essentially lay waste to the country and kill millions of people. The Qin emperor did the same thing. In fact, he buried these scholars alive in massive quantities around the year 220 BCE. This was really clearly the first cultural revolution. There were these competing schools of philosophy of how you should structure government and your life and the country. And the Qin dynasty represented the so-called legalistic school, which was the most severe, and there were incredible punishments for everything. It was then superseded by Confucianism, which then dominated. But there was also a school prior to that of Mozi, which much more than Confucius recognized the importance of technology for an advanced culture. But his writings were more or less disappeared because Confucius was officially adopted. However, there's a book called the Zhou Bi Suan Jing, the mathematical classic of the Zhou Drama, which the Zhou dynasty ended around 500 BCE. So just the name of it suggests that a tremendous amount of what they wrote down after the Qin dynasty had a much older history. It seems quite clear it must have had an older history. No one knows how old it was. So the history got erased by their own culture. Although they kept meticulous records of many things, they did not write anything down about mathematics prior to the Han Dynasty. So now the problem is that mathematics was not considered to be a particularly important basic discipline. It was really a completely utilitarian discipline. The only thing that was really important was astronomy. You did need to understand what's going on in the heavens, because the emperor was only a legitimate emperor if he had the mandate of heaven. So I'll come to that a little bit later. However, already in his Jobin Swung Jing, the Pythagoras theorem is stated, and a rather mysterious description about yellow and blue pieces and how Sumerian is described, which later on is clarified, and it's this diagram, which in and of itself is it's actually the 3, 4, 5 triangle. You see, the corners are right triangles. It's 3 this way, 4 this way, and that'll be 5 along the diagonal. So this is now, but if you think about this diagram long enough, you see that it's a proof of Pythagoras. It's by far the nicest proof. Here's how it's a proof. So up here, you take the central thing, which C is the length of the side, C squared is the area. Now divide it up with those 2 upper triangles and simply translate them down into the corners. You get that. One, you see, what's the side of that corner down there? That was the small side of the triangle, A squared. And the one there is B squared. So you've taken something whose area is C squared, you've just shifted 2 pieces, and lo and behold, it makes up 2 squares of size A squared and B squared. What's happening on the bottom? This doesn't seem... Oh, I see. I missed... Oh, yeah, okay. There's another proof here that you can take the entire rectangle and divide it up 2 different ways. And if you throw out the blue and the green, you're left in one case with A squared plus B squared, and in the other case with C squared. So, okay, so I think the Chinese, depending on how you date it, seem to have possibly the earliest, but it's quite, comparable to the Indian. It could well be comparable to the Indian discovery. Okay, well now of course we've got to come to Greece. So they did prove it, of course, and that's when Pythagoras lived, a little bit after Thales and before Euclid. Thales being often considered the person who really started the trend to do mathematics with Pythagoras, and Euclid who codified it. Now there's huge controversy as to the extent to which the Greek mathematics was stimulated by the Babylonian. There is this Assyrian Empire just at the time the Greeks who used cuneiform, and it's just at the time the Greeks were beginning to pull their civilization together, and then there's of course the Phoenicians, from whose alphabet the Greeks got their alphabet. So it's they were great traders. It's much debate. Okay, but the thing which is clear, without a doubt, is that was totally unique in Greece is that they loved proofs. Maybe they just loved to argue. They debate. But in any case, for one reason or another, maybe the discovery that square root of 2 is irrational. Anyway, they fell in love with proofs of things, and this is clearly their hallmark. And here's what it says. Argeometritos medius esito. Without geometry, nobody may enter. Euclid's first proof is the ugliest one I've ever seen. It's read Euclid's book 1, it's that thing on the left. Euclid's book 6, I think it is, has this proof on the right with similar triangles, and I won't go through it, but it's a very elegant proof. Okay, let me go on to talk about algebra. So, the Babylonians also invented algebra, in a sense. People say, what is algebra exactly? But almost all algebra, when you look back seems to center around absolutely screwball problems that no one would ever pose unless they were mathematicians. So I think algebra at the beginning was always an internal matter for training students and challenging students, and mathematicians enjoying the game after they learned it. So here's a screwball problem. And, okay, Babylonian problems also often have a geometric basis, but that doesn't mean the problem was geometric. How about I added the bricks, the laborers, and the days, and it was 140. The days were 2/3 of my workers, and it's a known fact that a worker can carry 960 of a load each day. Find out how many bricks there were, how many laborers, and how many days. Okay, I just go home. It's a quadratic equation that I did there. 1400 is laborers squared plus 50/3 times laborers. The solution is simple enough. 90 loads of bricks, 20 days, 30 laborers. But what more absurd problem could you have? Oh, God. Okay. Now, the Chinese, meanwhile, also, and this is really extraordinary, because unlike later worlds, actually the Chinese didn't pose absurd problems. They were much too utilitarian to be distracted by ridiculous problems. So there's this book here, in which, called The 9 Chapters, I think it should be correctly translated, 9 Chapters on Computational Methods, Swung. People translate it mathematical art, but that's much too fancy things. I think it really... Anyway, it was compiled in the Han Dynasty, presumably from earlier materials. But the Han Dynasty is the beginning of the incredibly rigid hierarchical bureaucracy which has characterized China in every single dynasty. Now, Chapter 8 is all about arbitrary systems of linear equations, and they solve these equations exactly the way it's in this thing called numerical recipes, which is my sort of Bible for numerical mathematics. Gaussian elimination, which only gets Gauss. I mean, come on, 1800. That's 2,000 years later. So here's a typical problem. 3 bundles of top grade paddy, 2 bundles medium, 1 bundle low. Yield, 39 dew of grain. 2 bundles top, 3 bundles medium, 1 bundle low. Yield, 34 dew. And then there's a third one. Tell how much paddy does 1 bundle of each grade yield? Well, okay, so T is the amount of yielded by top, M medium, L low. And we have 3 linear equations telling you how many dew come out from each type of grain. So, how do they solve it? Just like we do, by Gaussian elimination, rows and columns. And well, how do they do it? They do it with sticks. This is a Chinese woodcut, Japanese woodcut made, sometime, I don't know, in the 2nd millennium. But it records this technique, which was preserved over millennia without change. So you have this square board, and you put little black and red sticks. Red is the good color, so that's a positive number. Black is a very bad color, it's a negative number. Opposite or accounting. In any case, you fill in with the sticks, and they rattle around, and out comes the answer. Okay, so it's just like a computer. So there's the Chinese. It's so practical and so incredibly well done. It's mind-boggling. But notice, there's nothing like what we would call algebra. I mean, there are no formulas, there's no X. Okay, then along comes Diophantus in the Greek tradition. Now, he's a weird kind of exception, a complete anomaly. No one really understands even when he lived. It comes out of the blue, and his math seems to have almost no connection with the rest of Greek mathematics. But in Alexandria, they did all sorts of school things. They cut open prisoners in order to discover how bloodstream works and stuff. Okay, here's a typical problem from Diophantus. Define 3 numbers such that the difference of the greatest and the middle has to the difference of the middle and the least a given ratio. Further, that the sum of any 2 is a square. Well, why would you ask that? It's not clear, but they, again, he loves these problems. And he did have an unknown. This is the way he wrote it on the top line there with those weird notations. Now, literally, the triangle is, of course, the capital delta. It stands for dunamis, or square. So that's the unknown squared. Gamma is the third letter of the alphabet, so that's 3. Then this really funny symbol next to it is the symbol for the unknown. The iota beta, that's 12. Then M is a symbol for a constant. Beta is 9. EC or EC something, that means equal. And then square, equals a square. So in modern, it's the thing on the bottom. He's trying to solve that equation. Right. So he basically, though, has all of the rules for simplifying equations. The thing which really bothers him is he has only one unknown, and his problems are kind of complicated, a lot of them. And he has to stand in his head to do algebra, which is plain. But, okay, so there we have it occurring here. So notice, by the way, in the case of Pythagoras, we really had, China was the one that was independent, and the others might well have come all from the Babylonian. Now algebra, however, seems to crop up really much more independently in these different cultures. So we find it occurring in India in the middle of the first millennium, a little bit after Archimedes, probably. We don't know when. And this amazing, this is the most romantic story in the history of math. There's this poor farmer who's struggling along with a tiny patch of land in the Punjab, and he's plowing his field with an ox and this wooden plow. I don't think he even had metal. Struggling away, and all of a sudden, ka-chung, he hits something. Damn! Another rock. Okay, he digs down. It's not a rock. It's a huge bundle of birch bark, all wrapped up together. He's already destroyed about half of it by plowing through it. But he realizes, he looks on it, and all these squiggly things are written. He goes, oh my God, I'm in big trouble now. So he goes to the British collector, who's the local muckamuck there. It's the middle of the 19th century. And says, I found this thing. And this guy says, boy, that's weird. He sends it up to Delhi, and they send it. And now it's in the Bodleian Museum in Oxford. And it's deteriorated rather a bit. But nonetheless, there was enough that was preserved that they were able to reconstruct a tremendous number of problems. And this thing here, with the double lines around it, is a formula. And I've written below what the formula says. The unknown was this, this dot with a squiggle below it. And so this thing, 0 over 1, that's the unknown. And then 5 over 1. You know, 1 is the denominator, you see. It's, 0 is the numerator, but that stands for an unknown number. And then 5 over 1. U means add. And mu means square root. And then another number, unknown number. So you want to find a number x. When you add 5 to it, it's a square. If you subtract 7 from it, it's a square. Anyone know what that is? 11. 11 plus 5. Yeah. Okay. Anyway, then the whole thing gets the Indians really run with it. And what's interesting is that in India, numbers remains a sort of semi-religious occupation. It seems to be cultivated in 2 places in the first millennium. It's cultivated in large Buddhist centers. There were these large, we would call them colleges in a sense. They're centers of scholarly activity with a tremendous number of people trying to understand what Buddhism is all about. But there are also places where mathematics happens to be done. So there's a place, Takshila, which is down in Pakistan, and what's the other one? That's it. That's in India. And the other place where it's cultivated are by Brahmins. So like the Chinese, you see, the thing of paramount importance in both India and China was understanding what's going on in the heavens for astrological purposes. If the emperor failed to predict an eclipse, this was a tremendous black mark against him in China, a sign that he had lost the mandate of heaven. and he had to prove this wasn't true. So he spent a lot of money having an astronomy bureau which attempted to predict eclipses. Unfortunately, they were so algorithmically oriented that all their work on astronomy was centered around trying to find cycles in things and predicting things this way with essentially explicit algorithms. And that's incredibly hard to do because whereas the Greeks had understood that you have to look at it geometrically, and you can do this very accurately with these epicycles, and some version of this had spread to India. So the Indians actually were way ahead of the Chinese. I'll talk about contact there a little bit later. But in any case, the Brahmins in their temples, one of the things they had to do was to say you should get married. I mean, there's those auspicious things. You've got to know when the bride was born exactly in the hour when the groom was born, and then you could do all sorts of stuff and say you'd better be married on May the 23rd or something. So astrology was a huge thing, and to do astrology, of course, you needed astronomy. To do astronomy, you needed math. So the three subjects were inextricably bound to each other. As I say, this was connected to religion. The other thing which is really weird about India, which boggles the mind, is that they wrote stuff down in verse, Sanskrit verse, that was so compressed that it's essentially incomprehensible by itself. And these Sanskrit verses were memorized by the students. So they had this guru Shishya system. The student comes and says, "Please, master, if I starve on your doorstep for a week, will you accept me as your pupil?" That's the sort of apocryphal story. So in any case, once he would then explain what these things meant, but they had to memorize them at great length. And this continues to this day, this memorization in very Orthodox families, memorization of sacred Sanskrit verses. However, it was very successful. They went on, they didn't just, their initial variable was called yavat tavat, which means as many as so many, meaning you don't know how many. X. And then they said, oh, we need another one. So, okay, they used black, ka, for kala, black, and ni for nilaka, blue. A plain number was this rupa, which is like the same word as rupee. And here's another screwball problem. If thou be conversant with the operations of algebra, tell the number of which the biquadrate is the fourth power, thus double the sum of the square, and 2,000 times the simple number is a myriad less 1. So fourth degree polynomial. And it has tricks, of course. It doesn't have the general formula for solving fourth degree polynomial. It has tricks. All right. So then so now I'll go ahead more rapidly. Then comes the Arabs onto the scene a little bit later. Diaphantus is translated by the Arabs. It's not clear whether Al-Khwarizmi himself had Diaphantus at his disposal, but it is also that they had contact. See, what was happening in Baghdad was that they had this whole house of wisdom in which they were gathering scholars from all over the world, from Constantinople in the west, from India in the east, and bringing these people and having them translate their works into Arabic. So this massive translation program that goes on for 200 years. So in particular, it seems that Brahmagupta's work was indeed translated into Arabic about 20, 30 years before Al-Khwarizmi. And then we have Omar Khayyam a little bit later, continuing this tradition of algebra and geometry. And then we have very clearly the Arabic ideas spreading to Europe through Fibonacci. The year 1200, he traveled in the Middle East as a merchant and learned how the Arabs kept their accounts. Actually, Al-Khwarizmi is not so much about keeping accounts. His book, 2/3 of it, is about inheritances. I mean, I guess they really, the Quran has tons of stuff about exactly how you divide up somebody's wealth. and it gets very tricky. So algebra is indeed very useful, and that's really why it seems to be the real goal of Al-Khwarizmi's book. So, yeah, as I said, Brahma cooked this. This is the book, the Brahma's Fuda Siddhanta, which means Brahma's corrected treatise. Anyway, it's taken to the Caliph in 770. Al-Khwarizmi writes his treatise, but he drops the use of variables. He just has no symbol for variables, unlike Diophantus or the Indians. Diophantus is translated, again, no symbols. And then finally it goes to Leonardo Pisa, that's Fibonacci. Okay, and then but meanwhile in China, now this is the most extraordinary thing. The Chinese don't, there's this remarkable guy, so I have to explain, the ruling literati in China have to pass this incredible exam. Now what do they learn in this exam? They learn everything Confucius wrote. They learn the history of China in minute detail. They learn to write beautiful poetry and essays in classical Chinese. Some dynasties, there was a little part of the exam where they had to learn some math. But in other times there wasn't any mathematics in the exams at all. But basically, mathematicians were very low on pecking order, which was very precisely delineated. So here's this is a Song Dynasty writer who writes in the preface to his book, which is a beautiful book on algebra. He's doing it basically in his spare time because he loves the stuff. Perhaps my problems will serve as material for gentlemen of broad knowledge to peruse in their spare time. For although mathematics is a minor art, it is worth pursuing. But you see, in spite of that, they're discovering amazing algorithms. They're discovering how to simultaneously solve polynomial equations now, something which doesn't occur in the West until the late 18th century. So it's called what we call elimination theory. And this guy, Zhu Xijie, he was a wandering teacher scrounging out a living, teaching a little math to merchants who didn't know math. That's usually what you do. And the only reason his book survives is that the Koreans were more interested than the Chinese, and they printed it. So here's his book from Woodblock. So what's he doing? He's doing it with sticks, just like they were doing it before. But now the sticks are arrayed. You see, if you have you see this polynomial below in two variables. That's what this array of sticks up here in the middle top represents. You see, there's 2 there, and then this guy's. Yeah, the slash means it's negative. Wait a minute. Yeah, -8. Yeah, so along the top row are the powers of y. So these are the coefficients. On the top right is the unit. On the next to the left is the coefficient of y. The next to the left is y squared and then y cubed. And going vertically down, you get x and x squared. So anyway, it translates that way. This is called the method of the celestial element. Yeah, I thought it was kind of. Did I write this down? The four directions were named after. I don't know. It's Earth, Sky. I'm sorry, but anyway, it's the 4 directions from the center. Had names and were associated to these basic elements of the world. So it's very much intertwined with the whole kind of Chinese philosophy of opposition and of everything having a complementary opposite, without which it cannot survive either. There's a lot of speculation also as to whether the Chinese writing itself influenced the nature of the mathematics they did. I mean, the fact that it was logographic, like the earliest, the Sumerian cuneiform was also 1 character for 1 word, and then it went to a syllabic alphabet. and the Chinese stuck with the logographic approach. And some philosophers feel that this in itself, I mean, the fact that it's utterly uninflected, too, is, they take this as somehow controlling the way the Chinese viewed the world. It's sort of the warfare hypothesis. The language constrains your philosophy and the way you view the world. Okay, and then finally in the West, it's not really until Fermat and Descartes, it's 1600, that they begin to write down polynomial equations in two variables. So Europe was, without a question, was behind in these cases, but it catches up. Now I'm running out of time. I'll just very quickly. Calculus, likewise, is discovered in many different places. Let me see what I want. Oh, yeah. So I want to. Leo Hui should not be there. So Archimedes, I guess I put them both there at the same time. So almost integral calculus really is discovered quite independently in these three cultures and almost identical procedures. That's what's really stunning. I mean, Archimedes' proof was based on, first he is calculating the area of the sphere by dividing the sphere up into these narrow little peels like that, and comparing those to a little triangle that you see on the side. And in modern terms, he's really integrating sine phi. In fact, explicitly in Archimedes is the Riemann sum for sine phi. Word for word, it's exactly the Riemann sum. And we call it Cavaliere's principle. That if you want a volume, you can also slide things sideways to rearrange them, and the total volume will be the same. And he has another book called the Method, in which he uses the lever to do this fantastic number of rearrangements. So this is how Liu Hui and Zhu Gang in China worked out the volume of the sphere. First comparing the sphere to what was called the double umbrella, that thing with two, like the intersection of two cylinders going this way and this way. And then rearranging the exterior, which is the gnomon, into a pyramid. So I'm not going to go into that. So in any case, in the meantime, Aryabhata comes on the scene. As I said earlier, Greek astrology had gone to India, and a certain amount of astronomy with it. But the Indians went in a totally different direction. They had been, for a long time, working on Sanskrit grammar, and they were really into recursion and combinatorics and summing and differencing series. As I said, Alexander had brought elements of Greek learning to India, in particular a table of chords of circles, and the first use of differential calculus is, I think, is in Aryabhata, the year 500. So I'm running out of time, so I'll skip. All right, so here we go. Let me throw in a few more things that happened. Okay, okay, up here. The Silk Road opens. The Chinese, as I mentioned, were really big in making accurate calendars. When the Silk Road opened, they discovered that the Indians were much better at predicting eclipses. This is the Tang Dynasty. And 3 different Indian families moved to China, were given Chinese names, and worked in the astronomy bureau of the capital. And one of them wrote, in fact, an entire calendar based on Indian methods. But they were rejected. They were ignored. Jan Shaw and I have been studying this recently. Then the Mongols come. They have all of this fantastic astronomy from the Arabs. And in the Mongol dynasty, they're also ignored. And they write Kublai Khan has get these people together to write a new calendar, but he decides, let's not go with the Islamic one. The Chinese will never believe it. They have to write it in their own way. So they also ignore everything that came. And the most wildest hypothesis is the RSS believes that the Jesuits brought calculus from India India developed incredible calculus in around 1300 in Kerala, a man named Madhava, who really put integral and differential calculus together, found power series for sine and cosine, expansions of pi, very sophisticated math, really the full calculus of the circle and the sphere. But it seems very unlikely that it did. So, just to finish off, okay, in Greece, math was on a pedestal, without a doubt. And they had this fantastic library in Alexandria. In China, there's this powerful bureaucracy with math being a lowly craft in the hierarchy, a low pursuit as a hobby by some senior figures. Astronomers a bit higher. In India, there's this religious orientation, and many mathematicians were Brahmins who used the math for astrology. Right, so I think I've... And in Islam, well, Islam always was, in many ways, just a derivative culture. The translation was the big thing, and they pushed Greek geometry deeper. That's without a doubt true, but I don't think it's fundamentally different. One word that, it's true that Greeks, just to summarize this, don't try to read it, listen to me instead. The Greeks certainly invented formal proof, but the Chinese, without a doubt, were superb discoverers of algorithms, of computation without formulas, astronomy without geometric models. What mattered wasn't the method worked. In India, it was very funny. They didn't really like the idea of logical reasoning. They said it would just go on forever. You know, you can deduce this and this and this and this. Where are you going? But they really, what to them was the center of math was what they call the yukti, which is cognate with the English word yoke. You connect things with a yoke. And I think that's the way mathematicians today think. The best math is when you create a yoke that links something beautiful in this field with something beautiful here. They were very precise about analyzing exactly how they justified things, and tradition was one. Anyway, there's a few things that didn't never spread. I've held you for an hour, so.
Mumford would entertain one or two questions. Peter.
I think it's worth saying that your poems is Islam, you can't refer to Arab.
Yeah, we're Persians. Absolutely, they're Persian. Yeah, excuse me, you're right. I was conscious of that, but I forgot to say it. Yeah, no, I wanted to. Yeah. No, without a doubt, well, I didn't really have time. What happens when Islam begins to spread into India is that there's a large group of Brahmins that flee south. And that's why Kerala, which is a narrow strip of land between the mountains and the coast in the southwest, a lot of them come to Kerala and create this indigenous tradition, which is really unique. Meanwhile, in the north, certainly the Muslim astronomy is being absorbed, and they are really making a synthesis of Muslim and native Indian astronomy there.
One of the great contributions, of course, to Europe was to connect mathematics with physics in the time to the Galileo.
Yeah.
Do you see any of that in your theories?
No. I find that astonishing too, but no, I mean, to some extent, what I did is that it came, there's this man, Nicole Arem, the French scholastic, who began graphing processes varying in time. And people say he comes from St. Augustine, some philosophical ideas. But you can trace kind of a root of looking at things that way, looking at geometry, but as a process instead of as a static thing. And no, I have not come across anything like that in India or China. Islam.
Are there any precursors to the fundamental theorem of calculus in China and India?
No. No, I don't think so.
Yeah, so,
There's no, sorry, there's no precursor to the square root of -1. I think that's, this is a uniquely Western idea.
So I was going to ask about concepts of the continuum. The Greeks certainly had concepts pretty sophisticated in Aristotle. Even has
Yeah,
a discussion of contiguity versus continuity.
absolutely. Yeah, absolutely.
And he has this conception that it really can't be composed
Yes.
of points. And I wonder if there are precursors.
Yeah, that definitely exists in India. They also were fascinated with this passage to the limit. But they certainly didn't have the method of exhaustion. They had the equivalent of it. They had the method, they didn't formalize it. Yeah, and China, likewise, you see, once you begin to do integration, but the Chinese didn't even worry about it to the extent that the Indians did. There's at one point this explicit question: is the square root of 2 irrational or not? That arises as a question in Nilakanta, which is sort of marvelous, but they have no kinds of tools for saying anything about it.
what's the history of zero?
The history of zero is that the Babylonians used it. I don't know why people say the Indians invented it. In the early Babylonian tablets, that's the time I was talking about, when they needed a zero in a place value number, they left a gap. But sometime around 700 BC, you find tablets in which a dot is put there, just to make sure that people don't mistake it, because a gap might be small. So they began putting a dot there. And if that's not zero, I don't know what it is. I don't know why people say that.
Is that what the Romans used then?
I don't think so, no. I mean, this was a cuneiform thing. I know, I think neither the Romans, the Romans and the Greeks had hideous methods of writing numbers down.
Ptolemy an actual zero.
Yeah, so he went back and forth, right? Isn't he? And I looked closely, but in Archimedes, I think he uses someplace. He goes back and forth in his notations, I think. Is that right?
Well, thank you again for a wonderful lecture.